Greetings, everyone who joined here today. My name is Alexander Laptev, and I'm a research scientist and one of the developer of the NVIDIA NeMo Toolkit for conversational AI. And today we will give a brief overview of this toolkit. It won't be like too technical presentation. If you want to ask me some tough technical questions, you can do it like in the QA section. This will be more of an overview. We'll talk about the toolkit overview in general, then where to start with NeMo, then we'll discuss in more details its ASR, which is automatic speech recognition, text-to-speech, and natural language processing capabilities. Then, finally, we'll see how to get NeMo models from research to production. And that would be it. So let's start. Again, NVIDIA NeMo Toolkit is an open source toolkit for conversational AI. When we talk about, well, at least when we talk about conversational AI, I think about three main things: automatic speech recognition, natural language processing, and speech synthesis or text-to-speech. This is the three main components of the conversational human-computer interaction. So the NVIDIA NeMo Toolkit is built around these three areas. So for automatic speech recognition, we can transcribe words, we can do voice activity detection, we can identify the speaker, we can diarize and separate different speakers in case of overlap in speech. We have quite wide NLP capabilities with net classification, name entity recognition, questions and answers, and so on. And finally, after that, we can synthesize speech to generate an answer to a user. Apart from just the speech synthesis, we have voice and intonation control, which is quite useful in real-life applications to make your speech synthesis more expressive. So, diving a bit more into technical details, the NVIDIA NeMo Toolkit is built upon PyTorch and PyTorch Lightning, with PyTorch for, well, neural networks, and PyTorch Lightning to running the training of it, sometimes inference on scale. So the NeMo core built on these two frameworks, and then we have so-called collections libraries for the specific task like ASR, NLP, and TTS. Then for these collections, we have pre-trained models. And so with all this stack, you can build your own speech applications, or NLP, just NLP. We have quite many pre-trained models for many languages, like English, Mandarin, Russian, Spanish, German, and so on. For now, unfortunately, we do not support Armenian. If you're interested, why, then ask me this question in the QA section. But I hope we'll be there. We have quite plenty of ASR and NLP tasks at hand, like translation, big NLP, and things like that. So it can automatically check your semantic when you program with NeMo. And it performs quite well at scale. I think the NeMo is the most robust conversational AI toolkit to run it on scale. We put a lot of efforts for this. Of course, it can be run multi-node and multi-GPU. It supports quite many numerical formats like float16, TF, 32-bit float16, and so on. And again, it's an open source. So this is the link. And at the second slide was the QR code, so you can just try it. So it's fully open sourced. Great, isn't it? So why do you need it at the first place? why didn't you have this toolkit? Why not something else? And it's built around conversational AI, and so it is made easy to build and customize conversational AI models. So this is a one toolkit for the both the whole pipeline for speech recognition, understanding, and synthesis. You can train your models from scratch or via transfer learning, and I highly recommend you to do the second because it saves computation tremendously. So neural models. Actually, NeMo stands for neural modules, not the fish NeMo. It is. They are flexible building blocks. They are quite actually convenient to build your own systems with them. So it has module collections that are easy to use, so you can easily integrate them with your existing workflows, and it is also easy to export for deployment, which we'll talk later. So this is just a simple pipeline, how you do NeMo. So you pre-process your data, you set your encoder and decoder models, you set your loss functions, and then just run the training. It is quite simple. So now to NeMo collections. I mentioned this quite a few times. So you can see it as a scripts and a whole concept of scripts and pre-trained models for many conversational AI tasks. So you can see this. We have ASR collections with quite many models and loss functions, not only for speech recognition, but also for identification. We have NLP collection with, this is probably a bit outdated. Now we have not only the BERT model, we have plenty of them actually through the big NLP concept. It has some nice features like hiding face integration and stuff. A bit less languages right now for general NLP. It is a bit harder to fit the whole bunch of NLP tasks for now than, for example, ASR. And TTS again. So we have quite a mainstream things like a Takatron 2, fast speech WaveGlow, and our own things like TalkNet. So so again, modular. All scripts and examples are there. All pre-trained models are there. You can just use it easily and freely. So it works. Now, actually, where to start with this thing? So we have a concept of tutorials. So, for example, if someone familiar with toolkits like Caldi or ESP.NET, they have recipes. We have tutorials. It is Jupyter notebooks, which can be used locally on Google's Colab. It has quite wide covered area of the NeMo. So we have general concepts with NeMo fundamentals, then to how to construct your model, how to publish your model. Then for speech processing, practically for everything you need with speech processing. For NLP and TTS, again, this QR code, you can just scan it and see what is the contents there. So the link is here that represents this QR code. So it is tutorials. They quite easily, though I'm expert, for example, in automatic speech recognition, I still sometimes refer to those tutorials because they're great. And if you don't even want to do NeMo as itself. You can just use them like to just to study conversational AI. It still would be fine. So yeah, I highly recommend you to try this. So then to the automatic speech recognition, a bit dive deeper to this topic. Yeah, actually, automatic speech recognition well, evolved quite, I would say, huge with time. So like in 2020, we had like 4.7 word error rate. So yeah, for automatic speech recognition, the word error rate is the main metric of the model accuracy or model quality. So for example, like we got like from 4.7% of the errors to 3.0, which is quite huge. So LibreSpeech it is probably the most widely used, the most common test set to measure the performance of ASR models. So the 3% of error, it is actually, I mean, someone can say that, oh, this is still huge. I mean, this is still not practical. It is practical enough. It is actually more than, well, kind of and it is beyond human parity. So if you, for example, would try to listen to this test set and try to text what you heard, you will probably get a bit more than 3% of the errors. So for such cases, we have really like superhuman performance here. Apart from this kind of academic example, we have quite many pre-trained models for many like commonly used languages. So yeah, some well, CTC-based and transducer-based architectures here. So CTC and transducer are ASR losses. Won't be dive deeply there. So yeah, apart from the neural network models, as in like to just recognize speech as an acoustic model, we have language models based on statistical n-grams or neural language models to further improve the quality of the speech recognition. We have self-supervised models, if you heard something about this concept. Right now it's not only Wave2Vec 2.0, but our own developments there. We have this nice concept of adapters. So the concept of adapters, it is kind of a next generation of fine-tuning. So instead of like fine-tune your data, fine-tune your pre-trained models to your data and facing like catastrophic forgetting problem, you can just use these adapters. These adapters are some kind of attachable modules to your like main model, and you train actually them and not the main model. And then you just concatenate the results with your model, just as a simple addition. So yeah, if you ever like going to fine-tune your ASR or whatever NLP models, I recommend you to do this through adapters. So yeah, and soon we will have decoding with WFST graphs and the model confidence estimation, which is also the important thing for robustness of the model. So yeah, let's move further with my little demo that I recorded myself. So yeah, actually I tried to break our model here, and this NeMo is on Hugging Face. So let's see it. Come on.
This model transcribes speech in lowercase English alphabet along with spaces on the bottom. It is an extra large version of the former transducer model, which has about 1600 million parameters.
Yeah, so I recorded my speech and then type compute, and so this is my speech. It is actually accurate. I mean, it is exactly accurate besides the very last words parameters, because Actually, I blew it. I pronounced it not so great. So the next one.
No, it works pretty well despite my perfect pronunciation. But can't it recognize even specific words like PyData or Yerevan?
Yeah, I like this double really well because first of all, it said that it can't recognize. So, and I pronounced cannot recognize. It said like can't recognize. So it was quite fun. So I just gave later why it happened. And then words like PyData or Yerevan was like completely wrong. And again, this is one of the flaws of this, not the model itself, but the inference. So inference in Hugging Face, it is like, it runs just kind of a simple grid decoding procedure without any language model. And for this, we do want to have a language model because our model probably just haven't heard this word like PyData. I mean, it probably should actually heard Yerevan, but yeah, with PyData probably this wasn't the training data, so it misrecognized it. That's why actually we need the language models. So yeah, but again, the model is great. I just really tried to break it, and well, I succeed because I, I know what I'm doing. So anyway, let's move further with this. So actually, how to run it like at your machine or at a Google Colab. I mean, if you don't want to use Hugging Face. So yeah, there's just three simple lines of code here. So you import your NeMo ASR, you initialize your model by just passing the name of the model here. For now, I mean, for this example, it is a conformal transducer, extra large. And then you just run SR model transcribe for your data. And that's it. That would do it. I mean, at least for a single file or for like for a notebook. If you want to run transcribing of like many audio files, like in folder or something, you can do it like just from Python, like this one. So call the script transcribe speech, provide your model name and your audio data, and that's it. It will do the trick. So yeah, quite simple interface. I mean, just the 3 lines of code. Beyond automatic speech recognition, we have models like MatchboxNet for speech commands or keyword spotting. Then we have MarbleNet for voice activity detection. Voice activity detection is a thing that says whether someone speaks right now or not, like whether there is a speech on a recording or not speech, or maybe some noise or maybe just silence. So it has text normalization and reverse text normalization. It is quite an important thing for production, actually. I mean, this is not it had little attention of academia, this field, but for production, you got to use it because, like, for example, your model will not, for example, produce you like capital letters, for example, and you may probably need it for your inference because, yeah, people like capital letters. So, for example, inverse text normalization does that. And text normalization used for speech synthesis, for example. Like when you synthesize your data, you just like, you type it like as you are, I mean, just regularly. But you have to like pre-process it for this speech synthesis model, like drop all punctuation, reduce capital letters and things like that. Maybe transform numbers to words, for example. So yeah. And also we have tools like this speech data explorer. There's tools for dataset creation and analysis. It is quite convenient when you want to analyze your speech data. So yeah, you can find it at the tools folder and try it if you want to analyze your speech data. So yeah, now to TTS pipeline. So yeah, Our TTS, or text-to-speech or speech synthesis, is quite fast, so we dropped Tachytron 2 and we switched to parallel known autoregressive models, which is actually important because everyone in production wants to have fast speech, well, yeah, fast speech synthesis models. It is robust against duration and skipping and repeating words. It is expressive. You can control pitch and the other parameters of expressiveness. Again, it is easy to train, and I mean, just as everything in NeMo. And yeah, we have GAN-based vocoders and plenty of spectrogram generators here. So our mean opinion score is quite good. So mean opinion score is quite, I mean, it is how quality of text-to-speech is measured. So it is a human measured metric. So people listen to some recordings of real speech, for example, like this ground truth 8 audio, and the synthesized speech, and assign their kind of their marks, their scores, like how natural it is. So our, for example, fast pitch models and mixed TTS are quite close to the ground truth of the expressiveness and naturalness. So yeah, and it was quite a few parameters. This is how it looks like to start with speech synthesis. So a bit more lines of code than for ASR, but still, again, we have two models here, one for generated spectrum and one for transforming this spectrum into actual audio, so spectrum generator and vocoder, respectively. So yeah, you load them, you generate spectrum with this, for example, phrase like hi PyData, this is fast pitch, and hi GAN TTS from NeMo. And then you convert your spectrum to actual audio and save. So let's try to listen to it.
Hi PyData, this is fast pitch with NVIDIA TTS from NeMo.
Yeah. Not that expressive, I would say, but this is just because this is like this simple example. Like you could play a bit with the expressiveness and get well, get a sound like you want it. So yeah. Then finally to NLP. First of all, let's talk about the concept called big NLP. I actually borrowed this slide from the last GTC conference of NVIDIA. So the concept of big NLP is to have extremely large language model trained on some enormous amounts of data. And well, how to do this effectively. So, and then you can do some quite interesting things with such models. I mean, you probably heard some of them. For example, this is a joint Megatron and NeMo project of big NLP, but you almost probably heard GPT-3 models, something like this. So they're quite powerful, and actually they're so powerful that we can't even fathom how they're powerful, but we'll see about that. So yeah, why do we actually need large language models? Mostly because they are few shots and zero shot learners. What does it mean? You can start just without any training data at all for your task, and just use those extremely large models. I mean, of course, if you can run them. So you don't need data for your particular NLP task at all. Of course, you can improve it with a few examples. Then it will be a few shot learning And also, it's like one model to handle all tasks. So you can train or even like hard code a few heads for this like one model and just run inference for this one model and have like full stack of your NLP capabilities with this. So let's look at this demonstration, which I also borrowed from GTC. It is about Omniverse, if you heard that concept, and the Project Melon, and how we put a big NLP model to actually well, interact with the user using just a voice commands. I mean, interact like to interpret the intention of the user and do as he says, he, she, they. So yeah, let's see it.
How can I help you? You can change colors, cameras, environments, and more. Changing camera to side. Rear.
Correct.
Side. Yes. I can open the door. Open the door. Changing camera to driver. Close. Changing camera to three quarters. Painting car in white color. Sure, yellow. Black. The recommended color is red. Painting car in red color. Changing camera to zero. You are welcome.
Yay, that's it. Sorry for the recording being too quiet. I don't know, I'm not sure how to. Oh. Okay, well, anyway, that was the last demo, so yeah, sorry, I blew it. Anyway, so what you just saw here is a combination of the three, this big fields like ASR, NLP, well, NLU, in fact, language understanding, and TTS, combined in one application. So the thing is, we didn't like hard code like the commands and the answers. We just kind of wired some functionality like from some kind of a base, like from embeddings representing the desired commands to actual like functionality of this application, and that's it. So it is like completely like zero-shot learning. I mean, if we talk about the intent classification or question answering. So it is great. So I mean, you can prototype and build your own conversational-based kind of applications. I mean, applications with conversational capabilities. Just that easy. I mean, that's cool. I mean, at least for me. So then a bit, what can you do else with this large language models? So what you saw there, it is called an entailment. It is how to cast zero-shot tasks. So you can do prompt engineering, for example. So like say you have some task, but you don't have data for it. Actually, you can do some prompt engineering to extract like some generated but still quite accurate and natural sentences from such model and thus generate your training data just with prompt engineering. Then you can do this instructions tuning, for example. So suppose you have some taxonomy like on this picture with nervous system drugs, psychoanalytics, and things like that. So you have this system and you want to generate training data from it. So again, you can do that. So big NLP models can produce can transfer this to actual and quite meaningful and rational sentences. And prompting will be coming soon, probably. Maybe it's already there. I didn't check, unfortunately. But yeah, the capabilities are quite interesting, and this is a paradigm shift indeed. So yeah, of course, NeMo has neural machine translation. I mean, who doesn't have it right now? The models of it are mostly transformer-based. Like you see here, probably the most overused figure from the Attention is All You Need paper. Also, we have this perceiver-based encoders if you don't want to use just transformers. So you can use pre-trained encoders from Hugging Face into NeMo, like not only upload your checkpoints to Hugging Face, but use some external ones inside of NeMo. You can choose of multiple tokenizers, like Hugging Face tokenizer, sender speed tokenizer, you talking to me, or you can drop tokenizers at all and use byte level encoding if you know what you're doing. So you can do fine tuning on your domain specific tasks. There are a few multilingual models, so many to English and English to many. Again, just bilingual models, quite many of them. But again, unfortunately, we don't have Armenian for now. So, again, other tasks. Oh, 5 minutes, thanks. So, yeah. Again, intent recognition, slot fill and token classification, punctuation, question answering, and things like that. So, yeah, quite wide capabilities. We're almost done. Just only one slide probably left. It is how to deploy your NeMo models. Okay, say if you're from academia, you won't be probably interested in this thing. But if you are from industry and you trained or just downloaded your model, and you want to run it, then how to do it? Not with NeMo. NeMo is a bit more about research. But anyway, we have another tool called NVIDIA Riva. It is an accelerated speech AI SDK. It can be deployed like everywhere, like started from like multi-cloud setups to embedded solutions. It is not open sourced. Well, some of these parts are closed. Some of them are open sourced. But it is, again, free. So, I mean, if you want like enterprise grade support, you can always buy an enterprise version. But mostly the Riva is free. And apart from deploying NeMo models, Riva itself has its own models. They sometimes even better than NeMo models because they can use proprietary data. And checkpoints from NeMo are trained on open, on data with not prohibitive licenses. So yeah, and it supports streaming. It is Kubernetes friendly. And yeah, again, it has support. So where to start it? You can look at the NVIDIA Deep Learning Institute and try to search that their reverse speech API demo, and it will be there. So you can try it. That's almost it, but I think if I have just a minute, I want to promote you the next GTC conference of NVIDIA. It is quite like bright, colorful, interesting, sometimes even breathtaking. It's not like in some, I don't know, your scientific conferences. It will be at late September, so you can scan this QR or you can Google it and see it for free. Well, I mean, most of the times, those GTCs are quite fun. Thanks.